first graph, every edge is actually part of a cycle, so none of them are cut edges on their own. So because no matter what I cut, everything is still connected. I could try there, or I could try here. If I do both, then I have isolated E, but otherwise, with just one of them, I can still get from everywhere back to everywhere. So that's cut edge. Nice work. So a graph is complete if there is an edge from every vertex to every vertex. This graph is connected, but it is not complete because we would need to have this edge and that edge and that edge for the graph to be complete. And also A to go to E and D to go to B. And do you notice how these two edges cross each other in this drawing? So it's been proven that this is the complete graph of size 5, which, just so you know, is often written as K sub 5. This graph is not planar. This is just some fun little graph theory info. And what planar means is you can draw it on a 2D plane, which is why it's called planar, without edges overlapping. So there is no way to draw this without edges overlapping. It's impossible. You can try all you want. It's mathematically proven not to be doable. So, little exercise. Which of these graphs are complete graphs? Complete because we have a whole bunch of edges missing, even though it is connected. All of those are missing. And the second one, every single edge is missing. There are a whole bunch of them. And in this, it's only the second one that's complete. So if a graph has, so here, just for example, a little more math, this graph has 4 nodes. It has 1, 2, 3, 4, 5, 6 edges. If a graph has n nodes and it's complete, that means between every pair of nodes there has to exist an edge. So the way that's written in math is n choose 2. And what that works out formula-wise is n times n minus 1 over 2. So for example, for the 4 case, 4 times 3 over 2 is 6. And assuming there are no self-loops, for a graph to be complete, if it has n nodes, it has to have n times n minus 1 over 2 edges with no self-loops is the maximum number of edges allowed. Okay, so a little programming exercise. This is the last box in exercise 2, where you're going to say whether or not a graph is complete. So given the adjacency rules represent a tendency graph extensively later in this course, so I won't define that yet, but just something to keep in mind. Basically, how many things depend on that thing getting done. And there are a million other contexts in which these things are useful. So that brings us to the edge of the properties section. Next, we're going to talk about the big category of graph algorithms. Like the main one that you first learn when you're really learning about graphs are graph search algorithms. So graph search algorithms are helpful for finding files, navigating around roads when you encode them as a graph, and a whole bunch of currency conversion. So if you're going from the dollar to the euro to the franc to the whatever, there are 1,000,001 different search algorithms uses. And let's define the 2 main basic search algorithms. The first one is breadth first search. So in breadth first search, what you do is you go layer by layer. So breadth first, you don't dive deep, you dive broad. So this is the order that if you started here at 1, this is the order you would visit nodes in a breadth first search. So notice how we're going layer by layer. So we start at 1, then we see the layer 2, 3, 4, and then we see 5, 6, 7, 8, then 9, 10, 11, 12. So the order we see things really depends on how far things are from the entry node. We're never going to see, if we see A before B, that means that A is less than or equal to B in terms of the distance from the root node. So for example, 7 is 1, 2 jumps away from 1. So everything we see before 7, 2, 3, 4, 5, and 6, are all 2 or 1 hops away from 1. So whether or not we see 2, 3, or 4 first, that just depends on sort of the order that things are stored in. But we're going to see 2, 3, and 4 in some order before we see anything else in this graph. Hopefully that makes sense. A depth first search is kind of the mirror to breadth first search. So there we dive deep before we dive broad. So here we start at 1, and then we go to 2. And before we look at any of other of 1's neighbors, we're going to first finish looking at all of 2's neighbors. So then we go to 3. And before we look at any of 2's other neighbors, we finish looking at all of 3's neighbors. So that means 4. 4 doesn't have any neighbors. We're done with 4. Then we go back, and we still have to look at 5. Now we're done looking at 5. Doesn't have any neighbors, so we go back to 3. Then we're back at 2. Now I'm done. I still need to look at 6. No neighbors, back at 2. Then I can finally go back to 1 and continue on with the rest of 1's neighbors, so 7, and then 8, and so on and so forth. So depth first, you dive deep. So there are numerous differences, but BFS will always take you to the shortest path to every node. So for example, let's go back to the DFS example. Let's say that we had another node out here, 13, and there was a path from 1 to 13. With the way DFS works first, we're going to exhaust all of 2's neighbors, then all of 7's, then all of 8's, which includes 13, before we ever look at this arc. So in a breadth first search, you would have ended up seeing 13 would be 4. 1, 2, 3, 4. In a breadth first search, at a depth first search, we end up seeing it later. So that's sort of the key difference between BFS and DFS. They're both useful and given in different contexts. So a breadth first search on a weighted graph, shortest path here doesn't mean how many hops are there. It means the sum of the weights on the edges on a given path. And it's easy to convert from weighted graphs to non-weighted graphs. How would I convert a weighted graph to a non-weighted graph and a non-weighted graph to a weighted one? So a weighted graph to non-weighted, you just move the weights. Easy. If I want to convert from non-weighted to weighted, how would I do that? Going from non-weighted to weighted. And we'll see another way to go from weighted to non-weighted in a second. But let's think about non-weighted to weighted. How do I encode an equivalent graph from a non-weighted context into a weighted one? Yes, we would add weights to the edges, and we could just give every edge a weight 1. So if every edge has weight 1, then it's the exact same graph as before, but we just added 1 to everything, and before all the edges were considered equal, and now they are 2, they just have weight 1. Nice. So when converting from one lazy way to convert from weighted to non-weighted is to just remove all the weights, but if we want the graph to still behave the same way, if there's a weight of 3, for example, we can just insert 2 sort of made-up nodes in the middle, and then there's still a distance of 3 from A to B. So this is assuming the weights are integers and positive, and if they are, you can do something like this. So let's talk about Dijkstra's algorithm, which is sort of the most famous algorithm for finding the shortest path from A to B in a weighted graph. And the way it works is it keeps track of the shortest known distance to each node, and from the node with the shortest distance from the start point, recalculate everything next to it. If we found a new shorter path, remember that, and once you found the target, trace the shortest path. So here is a graph that we might look at with Dijkstra's algorithm. So we start at node 1, and we want to get to node 5, or A to B. And there's 0 distance to node 1. Then the node with the next shortest distance from 1 is 2. So I now know that it takes 7 to get to 2. Now, from there, I can see that it takes 10, and then what we would do is then see, now we have to visit 3 and 4, and we still have to visit 3 from 1 and 3 from 6. So if I visit 3 from 1, the distance is 9. And if I visit, first we expand all of 1's neighbors. And from 1 to 6, it takes 14. Now, the thing with the shortest path is node 2. So let's look at all of node 2's neighbors. To get to 9, to get to node 3, that would take 7 plus 10, which is greater than 9. So I keep 3 as 9 distance. And to get to 4, it would take 7 plus 15, which is 22. All right, so now the thing with the shortest distance I haven't yet explored is 3. So the shortest edge coming out of 3 is 2. 9 plus 2 is 11, which is less than 14. So now I can say that to get to 6, I actually only need 11. And to get to 4, it would be 9 plus 11, which is shorter than 22. So here, I only need 20. Now, the thing with the shortest distance that we haven't yet explored is 6. So to get to 6, I need to go 11. And to get to 6's neighbors that I haven't yet seen, I would do 11 plus 9, and that would take me 20 to get here. And then I haven't yet explored all of 4's neighbors yet, so I see to get from 20 plus 6 would be 26, would be more than 20, so I don't need to include it. So that's what Dijkstra's looks like. Dijkstra's is a little complicated. To keep track of which node to look at next based on what has the least amount of distance, it uses something called a priority queue, but that's a little outside the scope of this talk, but if you're curious, you can look up what a priority queue is. So let's take a look at what search algorithm code looks like. It looks a lot like the function we saw, is there a path between? And here is that code. So you keep track of where you've been so you don't loop forever. You then come up with a data structure to store where you've been, and originally where you have to go to. Where you've been is always just a set. So you then get the next thing in what you have to visit, so long as there's still stuff to get, which there always is at first. You always start with a source in there. If the next thing you're going to is your target, okay, you're done. Otherwise, so long as you're not going somewhere you've been before, you add on the new thing to where you've already been, because you're there right now, and so you don't visit it again. Then you look up all of the neighbors of that thing, and for every neighbor, you add that neighbor as something you have to visit. And what these 3 lines look like depends on the data structure. So and otherwise, if you've done all this and you've run out of places to go, then at the end you can say, hey, I had no path to get to target from source. So in a breadth-first search, we use a queue, and a queue is just like a kind of a line at the bank or grocery store or literally anywhere you ever line up. You add to the end and you pop from the front. So the first thing in is the first thing out. So if you're the first in line, you're the first one who's going to get served at a bank or whatever. So here's an example of the way breadth-first search might work. You start at A, so current equals A, and I have to visit all of A's neighbors, which is B, C, and D. Then I visit the first thing between B, C, and D, which is B. And from there, now I have C and D to visit. And then what you do is you now have to visit all B's neighbors, E, F, and G. And notice how when I do first in, first out, C and D appear in this list before E, F, and G. So I would explore C before I explore E, F, and G. There's a question in the chat about Dijkstra for how to not look at every single thing. And the way Dijkstra, you can show that you can stop early at a certain point once you have explored, once you've found your destination, because it goes in the order of the shortest path to it. And Dijkstra doesn't work if you have negative edge weights. So all of your edge weights have to be positive. And if all of your edge weights are positive, you can say, hey, once I find the first path to where I'm going, I'm done. If I'm calling correctly, I'm pretty sure that's right. It's been a while. Anyways, let's go ahead and then look at depth-first search. So depth-first search, the data structure you use to keep track of where you have to go, is a stack. So you can think of a stack like a stack of pancakes. You put a stack of pancakes on a plate, and then the thing that hits the plate first is the last one eaten. You eat the thing on top of the stack first. So stack, we say, is first in, last out. So you add to the front and pop from the front. Basically the front being the top of the stack. So you add there, pop there. In a queue, you add on here and then take out from the bottom, the first thing that you put there. So here's what that would look like in a graph. So you start with A, as where you're currently at. You have to visit all of A's neighbors. The first thing you visit is B. And then you add on E, F, and G to before C and D. So you have all of B's neighbors before C and D. So the first thing you end up visiting after B is E instead of C. So that is the way BFS and DFS differ. They really just, in terms of how you code it, they only differ in the data structure that you store where you have to go in. So the next thing we will do is you will program BFS and DFS. So that is going to be an exercise 3. And so I cut out the node coming from 2. Mark that as done. I can cut out the node coming from 3. Mark that as done. Mark out the node coming from 9, or edge, sorry. Mark that as done. And then the things within degree 0 are chapter 4. Not chapter 7, because I also need to read chapter 5 for that. And not chapter 10, because I also need to read chapter 6 for that. But then once 4 is done, now I can read chapter 5. That has in degree 0. Check that off. And then also I can read chapter 6, cut that off, and now I can read chapter 7 and 10. So that's Kahn's algorithm. And for the last exercise in the notebook, my favorite, I think it's the juiciest, we are going to implement Kahn's algorithm.